It's not like we missed too much. All right, cool. So let's go ahead and start off with example 3. We have these 2 vectors, and we're going to apply some various operations to either both of them together or one at a time. And so the first one, v minus u, well, the vector v is 4, 3, minus the vector u, which is -2, 5. And so the rule for this is when you subtract 2 vectors, well, you get a new vector. So I'm going to have this notation where it is component-wise subtraction. So the first components, so it would be 4 minus -2 for the first component. And for the second component, it would be 3 minus 5. So we're doing this component by component. And so arithmetic aside, this would just be 6, -2. So it's component by component subtraction in this case. And so your answer is a new vector. So you subtract one vector from another, you get a new vector. And that would be it. That's your answer. So for question 2, it's -5 times the vector v. So what's the vector v? It's 4, 3. So really, it just, when you multiply a number to a vector, you multiply each component by the scalar in this case. So it basically distributes. You could think about it that way. And so that's just -20 and -15. For the last one, just kind of throws everything together. So -2u, which u is -2, 5, plus 4, vector 4, 3. So order of operations still kind of applies the same way. We focus on multiplication. So -2 times -2 is positive. Oops. Let's try that again. +4, and then -10 plus 16 and 12. So hopefully that's not too much of a stretch. And then from here we can add the vectors together component-wise. 4 plus 16 is, of course, 20. -10 plus 12 is 2. And so that's all we do. So pretty straightforward. And it's not really too much trig. Really, the only trigonometry here is the fact that vectors are kind of a trig thing. And because of that, anything we do to them will be considered trig things, even if it resorts back down to arithmetic. If only we studied matrices in this class. That'd be pretty cool. But maybe another semester. Okay, so hopefully everyone's good. There's also something called the dot product. if you go into any applied math, you will definitely learn at some point what a dot product between two vectors is. And the dot product for any two given vectors has a formula. So the dot product between two vectors is a number. It's a number. So it says multiply the first two components together and then add that to the product of the second two components. And really, it's not too bad in practice. So notice, of course, the symbolism is just a dot, hence the name.
So is it basically like multiplying the two together and then adding an x and y, or like adding the two components?
I mean, you can think about it that way. It's just when you say multiply them together, you can't really multiply vectors together. It doesn't make sense to multiply vectors together.
So you're multiplying the components. So like
you're multiplying the components together, and then you're adding each separate component. Yeah. Yeah. And you might think, what is this number ever useful for? The dot product, in all actuality, is a good measure of really of how perpendicular two vectors are. That's really what it measures. Or it measures, it's a metric for orthogonality, which is just it's just a fancy way of saying how perpendicular are these things to one another. And that's really cool for establishing metric spaces, which I will never talk about in this class. That would be really cool though. But so from here, we have these two vectors, and we're going to find the dot product, which means our final answer better be a number. A lot of people on the midterm last semester would just put the product of the two components and leave their final answer as a vector. The final answer is not a vector, it's a number. It's just a scalar. So the answer for this, we multiply it component by component. It's 3 times negative 2. 3 times negative 2. So now when I use the dot in this sense, it's not referring to vectors, it's referring to a product of whole numbers plus the product of the second two. So, I mean, really this is just standard arithmetic. So what is that? That's negative 6 plus, so it's 50. And it might not make too much sense of how does 50 tell you anything about the perpendicular nature of two vectors. And the answer is it's kind of complicated. It's a complicated answer.
And we're not going to do a whole class to figure it.
Yeah, as fun as that would be, I don't think I could get through with that. Plus, I'd probably get in trouble for explaining real analysis in a trig class. So it's just 50. You get a number. And for problem 2 over here, it's the same idea. I mean, I think this is pretty simple stuff. So this is negative 1 times 3 plus 6 times 2. 9. I mean, that's truly it. I wouldn't imagine anyone has any questions about that. Now let's move it up to something even more interesting. The geometric interpretation of the dot product. All right, so this is a little bit more interesting. So in other words, you have two vectors out there somewhere in space. So two vectors, just let's say they start at the same spot and they do whatever. Sometimes it's really good to know what the angle between those two vectors is. Well, we have a way of determining that using this formula right here. So this formula will help you determine the angle between two vectors. So really the part I mentioned this I guess relation between the dot product and if two things are perpendicular. If two things are perpendicular, then their dot product is 0. And so what's kind of interesting here,
So that if it's 0, that'll tell you the angle's right there, if it's perpendicular.
well, if the dot product is 0, I mean, you don't have to know this. I'm really, really caught up. And I'm going really quickly through this, so I need to stall. So this is me stalling. So if vectors are perpendicular, then the dot product is going to equal 0. I mean, again, you don't have to know any of this. This is just, I'm stalling for time right now. Right? I'm going way too quickly through this. So the dot product is 0. So if the dot product is 0 over here, guess what? Then we have cosine of theta is equal to, well, everything's 0. Because the numerator is 0. And then you could take cosine inverse of 0. Guess what that is? It's 90 degrees, just like two perpendicular vectors. I know, it's kind of cool, I guess, relative to my interpretation of what is cool. But nonetheless, it does have some very interesting, extensions to how you can start to change the space of which you work in. You don't have to use an XY plane. You can use whatever you want. In fact, we'll look at stuff like that. It's actually, I think, the last section we look at before the final, or one of the last sections on polar coordinates. Anyways, that was a fun rant. That means nothing. Yeah, that's right. It'll all be on the test. Okay, so example 5. It says pretty much bring back all those angles that we had above and find the angle between them. So problem 1, the two angles that we had. So I'm just rewriting them we're just bringing them back. And we're going to find the angle between these two vectors. Now it's very helpful that in the previous example, we found the dot product already. So if anything, if we call this one u, the vector u, if that's the vector u, and this is the vector v, we already know that the dot product is 50, which is great because that's the numerator of this formula. So we could just replace that with 50. Now, the absolute value of a vector, does anyone happen to remember what that means?
It just be positive. And if it's the same value, just positive.
Well, it's not the absolute value of the dot product. It's the absolute value of a vector. Happen to remember what that is? It's from last class. See, we used we used it in the horizontal and vertical component stuff. See, there it is right there. I mean, they gave us that number, but hey, look at that. It's right there. It's the Pythagorean theorem, in other words. So this will be the square root of, well, 3 squared plus 7 squared, the two components of u. So what is that? That's 9 plus 49, it's 58. And then v, same thing. We can do the same thing with v. So what is that, 68? 68, 8 squared, 64, 2 squared is 4. Okay, so what we have now, we have cosine of theta is now equal to, well, the dot product goes in the numerator, square root of 58 for the first one times the square root of 68 for the second one. And then naturally, we could solve for theta by doing cosine inverse. So it's just calculator work from here. And I suggest that you do this in the calculator as well, because chances are some of you are going to get this wrong. And I'll tell you why in a bit. So hopefully you didn't get a domain issue.
I did.
You got a domain issue?
Yeah.
All right, I know what you did. Did you get a domain issue?
Yeah.
Did you get a domain issue? Did you get a domain issue? You got this one? All right, so why did some of you get domain issues? As in, why did some of you not put parentheses around the denominator when you put it in the calculator? So when you put it in the calculator, it's interpreting 50 divided by the square root of 58, and then multiplying that answer by 68. It's bumping the square root of 68 to the numerator, because the calculator is not very smart. It doesn't understand placement unless you use parentheses. So for those of you who got, all right, yeah, so I had a hunch. So you got to put parentheses around the denominator, or else the calculator, unless you have a super fancy calculator that does do the spacing for you.
It's weird, there's a lot of parentheses on that on the calculator.
Yeah, there's a considerable bit. Cosine inverse has its own, and then there's parentheses for the square roots, but then you need one for the denominator.
And then to close the whole problem out.
Yeah, really the calculator will close them for you, but it's always just good practice anyways. So that is the vector, or the degree between the two vectors. So did everyone get the right answer now? Cool. So let's look at 2. Bring these back. So here we can, I'll call this one U, this one's V. And go ahead and figure out what it's called, the magnitude of U and V, because we already know the dot products, or the dot product. So that's square root of 37. Square root of 13. We found the dot product to be 9. Now it's 9 divided by square root of 37 times square root of 13. First cosine of 9 divided by square root of 37 times square root of 13. So hopefully you put it in your calculator correctly this time and get 65.77 degrees. All right, any questions? So let's see. That concludes this section. I also need to assign this homework set for Tuesday. I went through these problems right before class, and they're really arithmetic, just like this. So this homework will also be due Tuesday. These problems are really quick. They're arithmetic. So in other words, 7.4 and 7.5 in the book. So I'll put this up at the top right here. So sections, so what are they called in the notes? 3.3 and 3.4. And 3.4. So sections 7.4 and 7.5 in book. Homework due Tuesday. So need to get a chance to collect them and grade them. And that'll be whatever day that is. 29th. So, all right, that's it. So there it is in writing. Cool. Well, move on to radians. Exciting, radians, radian measure. So I guess before I start rambling, this is, you want to guess what section this is in the book?
9.1.
It's 3.1,
Oh, wow.
going back to basics in the book. It's 3.1 in the book. So naturally all the problems come from 3.1 in the book. So really radians is another way of measuring angles. We've been using degrees this whole time in this class. We've been using degrees. We're going to switch to radians because, well, radians they don't look as nice. They're not as intuitive because, well, what radians do is they view the entire XY plane as fractions. People generally do not like fractions. So as opposed to degrees, which gives you some sort of magnitudinal idea of what a measure is based off of some arbitrary axiomatic definition of a unit circle. So 360 degrees. And from there, you can figure out the magnitudes from, I guess, partitions of the unit circle. So with all that aside, radians are more helpful, not just because they give us a different way of viewing angles. It's not like we're just making this new measuring system up, but more importantly, it's the same way that if you have a percentage, like 20%, if you were to multiply something by 20%, you don't multiply it by 20. You multiply it by 0.2. It's because the magnitude of the percentage is not something that we consider. We consider this alternative form. Radians would be considered the decimal version equivalent of degrees. As in, we normally do not like using degrees in arithmetic, like, hey, multiply that thing by 90 degrees. It doesn't really work that way. However, we can multiply by its radian conversion. That tends to be a lot more helpful, as we'll see in problems that come up. So that's pretty much the main focus, or what is it, Kelvin? I think they much rather you use Kelvin in computations than Fahrenheit for whatever reason, I don't know. But it's pretty much that idea. So the definition of a radian, it's a little bit technical at first. So an angle that has its vertex at the center of a circle. So basically, if you have some sort of vector in standard position, then you generate this central angle. A bunch of this is just a bunch of technical talk. Really what this comes down to is one of the more important things. So 360 would be one complete loop around the unit circle. And that is equal to 2 pi radians. So we're going to be using pi a lot in this class now. But a mere mention of radians, we will be using pi a lot. Because naturally, its inherent connection to circles. And as such, this gives us an idea of what one full revolution is. So now you will start to, as you go through these problems and see radians as well, you will start to need to make comparisons between, I thought I fixed that. I fixed that in my notes.
Oh my God, that was bothering me the whole time I was looking at it. I was about to ask.
I swear that
Me
is,
too, I was like,
that is fixed in
that's
my
not
notes.
180, I'm pretty sure.
I was looking at it, I was like,
I was
why? My next question was, why isn't 180 opposite of 360?
Yeah, I don't understand. It is fixed in my notes.
Look, radiant actually swaps the 180 and the 90, just so y'all,
Just in this
just in
one
case y'all were
It
wondering.
was making me mad. I was like,
We're gonna,
I mean, I can make a formula and make that true.
fine.
If you gave me like 2.5 minutes and a Monster Energy drink, I could probably
So is it,
figure it out.
is 180 equal to pi and 90 is equal to pi over 2?
Yeah, so exactly as it's written there. So those of you at home, this is how it should be. It's corrected in my
Dude, it
notes.
was bothering me. My next question was literally, why is 180 not opposite of 360?
Well, I'm glad we got that figured out. Or maybe I should just leave it. Why not? Yeah, just leave them. Okay, definitely not. Now it's bothering me. 180 degrees is equal to pi, and 90 degrees is equal to pi over 2. So now we normally like to consider the quadrantals. They are important angles. So really in our minds, we always considered the quadrantals. If we saw them, we had to approach them in a different way. So you had 90, 180, 270 engraved in your head, hopefully. And now you also need to allocate a little bit more space in your head for their radian equivalent forms. Pi over 2, pi, 3 pi over 2, and 2 pi. And notice kind of the fractional way in which this is approached. See.
They're all over 2. I mean, it's just, that's 2 pi over 2, right? Which would just be 2's cancel and it's pi.
Yeah, it's every time you jump, instead of jumping 90 degrees, you're jumping pi over 2 radians. And yeah, pi over 2 plus pi over 2, that gives you pi. And always, when I do arithmetic, as we'll see later, I never really treat the arithmetic with the pi in it. I treat it as the underlying fraction. We'll see it in the next example, and then I throw pi in at the end. So I always treat this as a fraction. So I would look at this, and you'll all see this in the next example. I'll treat it as 1/2, and then I'll throw in pi right at the end. That's really the best way to look at these, because putting pi in your calculator is going to have a fit, because pi is an irrational number. So it's good to not put pi in your calculator unless it's contributing towards this final, irrational solution. But that was a good way to buy some time. Okay, cool. So for okay, the wording here is a little funky. This is also true for quadrantal angles. You can do this for quadrantal angles. It's just meaning, well, we figured out the quadrantal associations, but what about the non-quadrantal ones? But these work for quadrantals as well. And this may look technical, or it may not, but it means if you want to convert from degrees to radians, well, you take your degree measure, that's what this is, so maybe 135 degrees, you multiply it by pi over 180. And then guess what? You get your radian. To convert from radians to degrees, you take your radian, multiply by 180 over pi, you get your degree. That's all it means. And it'll make a lot more sense in application. But in other words, the way I like to think about it, because the main problem is getting these two rules mixed up, the way I like to think about it is if you want to go from radians to degrees, you have to divide out the pi. That's always been the way I thought of it, to get them straight in my head. And then if you want to go from degrees to radians, you multiply the pi in. So, or you can use whatever way you want to do it. In any case, look at example 1 here. So it says just convert from degrees to radians or radians to degrees, and it doesn't matter, or well, it does matter, but they don't really give you which one is which. So for problem 1, hopefully it's clear that 2 pi over 3 is a radian measure. So how do I know this definitively? Because it may seem kind of intuitive. Really, you might want to think about problem 4 while I go through these, whether that's a radian or a degree measure. But in any case, this is a radian. And we're going to convert this to degrees. So what do? We take the radian. We want to multiply it by 180 divided by pi, and we'll get a new number. Now, it's convenient. Like I said, I like to treat these as, I don't like to consider the pi's. In this case, the pi's cancel, so that makes it even better. If you do it in your calculator, the pi's will cancel anyways, but it's 2 times 180 divided by 3. You get 120 degrees, and that's it. That is it. So for problem 2, this is obviously a degree measure because there's a degree symbol. So we're going to convert 315 degrees to radians. So we're going to multiply that. So we're going to use this top rule. We're going to multiply it by pi divided by 180 degrees. So if you put this in your calculator, that's going to be a big mistake. because you will get a very not glorious decimal. So that's why instead you really want to look at this as 315 divided by 180 and then the pi. That's really the way you want to take care of all the numbers and then throw the pi in at the very end. This will come up quite a bit, so definitely want to get familiar with this as soon as possible. So 315 divided by 180. And when it says exact answers, I am going to want a fraction. Whether it's an improper fraction or simplified, whatever the case is, I want a fraction, a simplified fraction. I'm just making that clear now. I will be going off of that for the rest of the time I talk about radians. So 315 divided by 180. So 1.75, and I'm going to convert that. So that's 7/4. And now I can throw the pi in at the end. So pi over 4. So there's these different formatting things, as in fractions are nicer to look at than the decimal forms. This means, yeah, you should probably figure out how to move between decimals and fractions in your calculator.
I just figured it out.
It's very helpful.
I haven't.
We will be using it quite a bit. If you don't know, I'll help you after class or something. So other than that, that would be the radian measure. So this would be, so the same thing, it would be the same exact thing to say 315 degrees or 7 pi over 4 radians. It means the exact same thing. So negative 270. That's degrees. We need to convert it to radians. So to convert this to radians, we need to multiply by pi over 180. Again, I'm going to look at, really I'm looking at the numbers here. And then I'll throw pi in at the very end. So negative 270 divided by 180. I get negative 1.5, but I want to convert that to a fraction, an improper fraction. So I get negative 3/2. Of course, I left that little space because I'm going to throw pi in right at the end. So it'd be negative 3 pi over 2 radians, or rads, exactly. Exactly. I would make a joke about how it's rad, but I am a mathematician. It doesn't really fit our vernacular too much. And so finally, we just have 1. Just 1. Just 1. Is that a degree or a radian?
Radian,
Why is it a radian?
because there's no degree symbol.
Yeah, that's it. There's no degree symbol. That's all. That's all there is. So this is a radian because there is no degree symbol. And now this problem also helps because we're going to learn what 1 radian is in terms of degrees. So really, what is the most simplistic conversion possible? 1 radian to blank degrees. So 1 radian, since this is a radian, we have to multiply by 180 divided by pi. And so if it were an exact answer, there's not really anything to do. This would be an exact answer. I mean, it just seems kind of simplistic. and then you would put degree. But let's figure this out as a decimal. Probably like 57 something. 57.30 when you round up. We'll just round to 2 decimal places, it doesn't matter.
So those were a test question, would you want it in decimal or in fraction?
I'd specify.
Okay.
All right, so example 2, we're gonna convert the special angles from degrees to radians. So we're all familiar with these special angles because of the triangles, the special triangles. So that means we're going to need to keep in mind special radian measures now. Oops. So to convert this to radians, really that's just 30 divided by 180, just 3/18, that's 1/6. Or if you do that in your calculator, 30 divided by 180, convert that to a fraction, you would get 1/6 when you look at just the numbers. And then you throw the pi back in, but the 1 doesn't really do anything, it's just pi/6. All right, let's do the same thing for 45. So again, converting from degrees to radians. It's just 1/4. And then we throw the pi back in. But again, the 1 doesn't really do anything. It's just pi/4. $60 divided by 180, probably just 1/3. Throw the pi back in. The 1 doesn't really matter. So really, we're getting some important associations here that are probably worth comparing. Oops, missed one. So we are starting to get these important associations that we will need to keep in mind. It would be beneficial to keep these in mind, which the reasoning why will be more apparent as we continue. I'm afraid if I go any further, I'm gonna have nothing to talk about the next time in class. I have to stop class right now. I'm getting really far ahead. I just have to call it a day right here. So next time in class, I'll be able to finish up the rest of this. I need something to talk about. So
Are we going, so everything up until chapter 5 will be on the midterm?
everything up to radians is on the midterm.
So this won't, radians won't be?
Radians isn't on the midterm. You said up to chapter 5. I'm sorry. I'm just failing today. Yeah, everything up to chapter 5. You're right. So up to not including chapter 5. So this would be the midterm up to page 36 in the notes.
Yeah.
And I'll finish that next time in class. So the fraction, Lily, is if you have 1.5 in the calculator, if you press second and press that PRB button, that'll convert it to a mixed fraction. That's not good enough. So if you press second, instead of PRB, you go down one more time. So instead of PRB, just go down one. And you press that. That's how you convert from decimal to a fraction, at least with this calculator. So hopefully that helps. Yeah. All right, well,